What I want to discuss with you today is the following. When you're doing triple integrals, at the end you have some function maybe you're integrating, which is a function of x, y, and z possibly. There's a little thing at the end here that says dv, which means a small change in volume. And when you're dealing with rectangular coordinates, which are sort of the easiest to deal with, I attempted to draw a picture for you here, but typically we think of this as dz, dy, dx. And if you think of each of these little components as a small length, then you're doing a length times a length times a length. So conceptually, you know that this is a volume. That's easily seen here. So for example, this little piece of this little box is a small change in x, so it would be good to call that dx. Let's use a different color now. Let's use blue. This small piece of our rectangular prism or box is in the y direction, so we'll call that dy. And then let's use maybe, I guess we'll use green. And then this solid height here is in the z direction, so we'll call that dz. So it's easy to see that the product of all three of those things would give you a small change of volume, usually notated as, you can see up here in the upper right-hand corner, dv. Okay, so when we move on to spherical coordinates, we have a slightly more complicated picture because we're moving a distance away from the origin, which we call rho. And so that makes at least part of our little dv, this red box dv, we can say that this part of it here is d rho. And that's fine because rho is a distance, everything's okay. So that we know that's going to be a factor over here somewhere, d rho. We run into a little trouble because if we try and put, say, for example, d phi here, then that's an angle. And d rho, as we mentioned before, is the distance. So multiplying a distance by an angle is a bit of a problem. And then to make it worse in the case of spherical coordinates, d theta is another angle. So we need to do something to use theta and phi to get a handle on what the other two dimensions of this box are. So we need to make a decision which one we're going to go for first. I'm going to go for this dimension here, which I'm highlighting in blue. And the reason I'm doing that is that the length of that would be the same as the length of this little shadow here. So some fun things to realize that help us a lot with this. Number one, this little angle in here, that small tiny angle in there, we can call d theta. And the question is there a relationship between d theta and the length of this arc out here that we really want to find? And the answer is yes. We know something about angles and radians. So if you have a circle, it's a terrible circle, but you'll have to forgive me, and you have a length of a radius and a central angle theta, and this is the arc out here, then there's a relationship that holds that can help you with this, and that is that the central angle theta is equal to the length of the arc divided by the radius. Hence the term radians. It's sort of measuring the number of radii you can lay out along the circumference of a circle. How many radians are there? Sort of a good way to think of it. So we could do the same thing here if we consider the following. If we consider this, this triangle that contains d theta in it. So I'll attempt to trace over it. Here we go. With these little yellow dotted lines. And you can see here that there's like a triangle-esque figure that I'm drawing. And the only problem is I really need to know the length of the bottom of this thing. So let me show you what I mean. So I'll get my pen back. This angle up here is phi, and that's because of alternate interior angles. You can see alternate interior angles. I'll temporarily draw this and then I'll erase it. But this is two parallel lines here cut by a transversal. And then you can see the alternate interior angles here and here. All right, so I'm going to erase all that because it's going to ruin my picture. But I need you to see those alternate interior angles. And additionally, you also know that this distance along here is rho. So that's also rho, just like this distance is rho. So I'm going to erase that too. And again, I don't want my picture to get too cluttered. But then we can write a relationship here. We can say that the sine of phi is equal to opposite, which I'll call r, which is this little piece down here, over the hypotenuse, which is rho. So then we have that r equals rho sine phi. So I can get rid of the little letter r here, and I can replace it with rho sine phi. So that's looking pretty good. And then if I use this idea I have over here, putting little checks next to it to bring your attention to it, then I can set up another relationship. I can say that d theta is equal to that arc divided by the radius, which in this case would be rho sine phi. And if you solve that for the arc, you get that the arc is rho sine phi d theta. So what does that mean? It means that we have another contribution to our dV over here. We can put rho sine phi in there. So we're getting there. We're happy with this because an arc here has a length, and this has a little length up here, and here, and here, and here. And that means we're starting to build a volume. We have d rho here times the length of these little blue arcs. So now we have two things that have been converted to distances. So I can not worry about that sine angle anymore because these two things multiplied together give you a distance. All right, so we still have to deal with the d phi problem. So it's going to be our next issue. So it turns out this problem's a little bit easier to deal with. I'm going to draw another, let me get my line function here. There we go, go on my line tool. And let's draw another, let's undo that. Okay, forgive the pause there. Now I have my colors corrected. So I'll draw a line here, top to C. And I'll draw a line here, which is also top to C, and here to C. And what you can tell now is I've got another little triangle in there. And let's use a different color. I should really switch colors here. I'll just trace over it again real briefly. So here it is. It's this triangle. That's what I'm trying to show. I did it with the green. And then you can see in here that this little angle there is a d phi. And we also know that this distance here is rho. So if we go back and utilize this idea up in the corner again, then we can say the following. We can say that d phi equals another arc, which are these purple arcs, over the radius, which is rho. So that's rho d phi. And that's great because then I could just add another row here or multiply by another row to get our factor. So now that's a great thing. Actually, I should use the color green to match the other piece. That means that we can erase the fact that this is an angle now because together these two factors are now at distance as well. So when everything's said and done, dv for spherical coordinates is rho squared sine phi d rho d theta d phi. Of course, you have the option to consider the other 5 orders for there. So this is your correction factor.